Hi. So, happy snow day. If you go on Edmodo or on my page, whichever you use, there's going to be this handout that I'm going to use for this. It's about the law of cosine, so if you want to print it out or follow along, whatever. But I'm just going to use this so I don't have to keep redrawing this diagram. Okay, but what we're going to talk about today is the law of cosines. And what the law of cosines is it's pretty much the Pythagorean theorem, but for non-right triangles. Okay, so it's going to be the same kind of problem that we would use the Pythagorean theorem for. We have two sides of a triangle and we want to find the other side. But like I said, this is for when the triangle is a non-right triangle, or the formal term is an oblique triangle. Because remember that the Pythagorean theorem only works for right triangles. Okay, so it's called the law of cosine. So obviously we're probably going to use cosine somewhere in here. So let's get started. And this specific handout is deriving the law of cosine. So this is kind of like proving it, showing where it comes from. So we're starting off with this right triangle, or this non-right triangle, triangle ABC. Okay, and let's just take a minute, refresh our geometry, I guess. So if you look at triangle ABC, notice that here is my vertex A. All right, that's also going to be angle A. And vertex and angles are used with capital letters. If we look directly across from that angle A, that's going to be the side that we label with a lowercase a. Okay, the same thing is going to happen for B. Up here is going to be my vertex B. It's a capital B. It's also the angle B. And if I look at the side across from it, that's going to be labeled with a lowercase b. And the same thing is going to happen with C. So here's my capital C. That's the vertex C. That is angle C. And if I look directly across from that, this side over here is going to be labeled with a lowercase c. All right, so let's erase that. So, like I said, ABC is a non-right triangle. So what we're going to do is we're going to construct the altitude H that's going to go from B, and it's going to drop down, and where it hits, we're going to call point D. All right, so I'm starting up here at B, and I'm going to construct this altitude. And where it hits is going to be D. Now, we can always construct altitudes. You guys learned that in your compass constructions in geometry. But the nice thing about constructing this altitude is when we do that, remember, altitudes form right angles. So we just took this triangle that we really don't know anything about. We don't really know how to work with it. And we changed it into these two little right triangles. And by having right triangles, we can use the Pythagorean theorem. We can use SOHCAHTOA. We can use all those awesome things. All right, so if you look, when I dropped in that perpendicular, now I've got, hold on a sec. Now I've got this right triangle over here. And I've got this right triangle over here, both of which are fair game to use SOHCAHTOA and the Pythagorean theorem. So, and also notice that when I drop in that perpendicular H, really, when I dropped that in, I broke B up, the side of B. Remember, because B was this whole length down here. Well, this altitude cut it into two separate pieces. All right, and for this example, I'm going to name those separate pieces. So while this whole big thing is B, we're going to call this little nugget, if you will, this little nugget over here, we're going to call that X. Let me use something besides yellow. We're going to call this X. So whenever I talk about X, I'm talking about that little piece of B. And whenever I talk about Y, Y is going to represent this piece of B, all right, because I have these two pieces after I dropped in that altitude. Okay, so now that we know what everything is, so in that little paragraph on the right, this is what I'm using right here. So using right triangle trig, we can see that the sine of C is equal to H over A. So here's my angle C, and remember, I'm looking in this right triangle right here. Sine is opposite over hypotenuse. So here's my opposite, here's my hypotenuse. So yeah, it is H over A, I'm sorry. And if we solve for h, or we get h by itself, you multiply both sides by a, and we get that h is equal to a times the sine of c. All right, so that, I'm going to write that in. So in h right here, we can say that this is really equal to a, that's a horrible a times the sine of c. I'm going to make that smaller. I'm just not even going to write it. You guys can read. So a is equal to the sine of c. We can do something very similar to find out what y is. Okay, because y is right here. And notice if I do the cosine of c, all right, the cosine of c, I'm still in this triangle right here. And cosine is going to be a over h, adjacent over hypotenuse. So you get that the cosine of c is equal to y over a, multiply both sides by y. I'll write that out. Cosine c equals y over a. So if we multiply both sides by a, that's how we get this. Y is equal to a times the cosine of c. Okay? And remember, x and y were from when we dropped in at altitude and broke up b into two separate pieces. So if we think about it, x, this piece over here, x, is really equal to this entire piece b minus this y piece. Okay? So that's what this part says right here. X is equal to b minus y. So that little yellow nugget, x, is just equal to the big piece minus y. But we just found out what y was equal to, kind of. All right, we know that y is really equal to a cosine c. So if we substitute that in there for y, we get that x is equal to b minus a cosine c. All right, so this kind of looks like a lot, but really after we dropped in that altitude and labeled it, h and x and y, we just used some right triangle trig in this blue right triangle right here. So we just used some SOHCAHTOA to solve for h and y. And then by doing that, we could solve for x. So now that's actually kind of nice because we had these x's and y's and h's floating around, but we were able to make them all have a, b's, and c's in them. So we kind of got to take out all those extra variables that we added in. So what I'm going to do is I'm going to scroll down, because when you scroll down, it's the same triangle that we've been using, except now instead of x's and y's and h's, it's substituted in what we found for x and y and h. So instead of x, we have b minus a cosine c for that little piece, which we found above. Instead of y, we have a cosine c, which we found above. And for h, we have a sine of c, which we found above. Ooh, that's a lot of colors. There we go. All right, so just relabel the diagram, kind of cleaned it up a little bit. Now, if we look, we could, I guess we could pick either right triangle to use the Pythagorean theorem for, because I have two baby right triangles, right? I've got this one over here, and I've got this one right here. So either of those are fair game to use the Pythagorean theorem for, but I am just going to do it on this one right here. So we're going to use the Pythagorean theorem on that. So if I do that, that is where I'm starting off on this line of algebra right here. So if I do that, I know that c squared is really equal to a sine c squared plus b minus a cosine c squared. So it looks messy, but it's just the Pythagorean theorem. Okay, so let me scroll down here. It's very messy not having my smartboard. Scroll down. There we go. All right, so this is just using the Pythagorean theorem. So here I am But really, we can totally simplify this because it's just squaring stuff. So when you square this first piece, a sine c, well, that's just a squared sine squared c. Okay, and then when we square this part on the right, okay, that is something that you're going to have to FOIL because that's really b minus a cosine c times b minus a cosine c. So you're going to have to FOIL that or box it, whatever you want to do. But after you do that, that's what gets us to this line right here. All right, so that's after you FOIL and combine like terms. Okay, now just for fun, what I'm going to do, and I guess it's not really just for fun, all right, so what I'm going to do is I'm going to take this minus 2ab cosine c, and I'm going to move it to the end. All right, and the reason I'm going to move it to the end, and we can do that, all right, as long as you take the minus sign. When I move it to the end, that's really nice because right down here, oops, because right down here, if I look with that 2ab cosine c on the end now, it's right here. If I look at my first two terms, the a squared sine squared c and the a squared cosine squared c, I have a common factor of an a squared. Okay, and really you should kind of pay attention to that common factor because since I have a sine squared c and a cosine squared c in there, you should recognize that that looks really similar to the Pythagorean identity. All right, so if we factor out that a squared, which is what happens in the next line down here, I do have a sine squared c plus cosine squared c in parentheses, which is awesome because sine squared c plus cosine squared c is really just equal to 1. All right, so this bit in parentheses is really just 1. So what I found is that c squared is really equal to a squared plus b squared minus 2ab cosine c. Okay, so, and notice this part right here is identical to the Pythagorean theorem. All right, so like I said, this is really close to the Pythagorean theorem, but since it's a non-right triangle, we've got this little extra junk, which involves a cosine, which is why this is called the law of cosines. Okay, and notice we did this for when we were solving for c squared, but we could also do something very similar solving for a squared or solving for b squared. So if you look on the identity sheet that I gave you, that you guys are able to use on the reference, that you guys are able to use on the Regents exam, sorry, it gives you 3 laws of cosines. So it gives you the version for when you're solving for C, which is this. It gives you the version for when you're solving for A, and it gives you the version for when you're solving for B. So what I want you to do is after this, I'm going to post a couple of examples from Khan Academy of them using the law of cosines to solve some stuff. And so I want you guys to copy those notes and also take a post-video quiz. All right, and I definitely have enough time. So what I'm talking about with those formulas is we just did c squared equals a squared plus b squared minus 2ab cosine c angle c. If I was doing this for a squared, that would be b squared plus c squared minus 2bc times the cosine of a. And if I was doing this for b squared, that would be a squared plus c squared minus 2ac times the cosine of b. Whatever you're solving for, whoops, undo. Whatever you're solving for is always the angle that's in your cosine, and then all this middle stuff is just using the other two sides. All right, it's the same down here. What you're solving for is the angle that you take the cosine of, and the inside is the other two sides. All right, so go watch those other videos por favor.